The active site. The active site is the part of the enzyme where the actual chemical reaction occurs, and so the substrate binds the active site and then is chemically reacted upon. And here we see a space-filling model for the enzyme hexokinase. The substrate, glucose, enters the site and binds. The enzyme then changes its shape, and we call that the induced fit model. Whereas the substrate binds and then the enzyme contorts its shape to have the perfect shape, and then the reaction occurs. So an enzyme must attract and bind the substrate. Once the substrate is bound, a chemical reaction is catalyzed. This two-step process is as follows. The enzyme and the substrate combine to form the intermediate, the enzyme bound to the substrate. Then that decomposes to produce the enzyme and the product. The enzyme-substrate interaction. Each different enzyme has its own unique active site, whose shape determines which substrates can bind. And again, enzymes are said to be stereospecific. They may bind one optical isomer, but not another optical isomer. And so when you want to specifically produce stereoisomers in chemistry, you must use enzymes, because normal, traditional chemical methods are not stereospecific, but enzymes are. So humans only will make or use L amino acids, never D. The lock and key hypothesis states that the substrate is a key that fits into the appropriate active site, whereas the induced fit hypothesis states that the active site adjusts its structure before the reaction can take place. And a lot of enzymes do use induced fit. So the correct substrate fits the active site, and then that causes the enzyme to have a conformational change to start the chemistry. And so in a way, both are kind of correct. An enzyme, the molecule has to be the right molecule to fit in the first place, and so that's like lock and key. But then, in addition to that, the enzyme does change conformation to initiate chemical reaction, and so that's in the induced fit model. And so what we really see happening has components of both the lock and key model and the induced fit model. Enzyme-substrate interaction. Here we have proximity catalysis. The enzymes bring the reactants close together. The productive binding hypothesis. This explains how the enzyme works to make sure that the correct bonds are broken and formed during the reaction. And the strain hypothesis explains how the enzyme forces the substrate to change shape, which allows catalysis to occur. So the molecule binds, then the enzyme itself changes shape, forcing the molecule to change shape, pushing strain on its chemical bonds, which then allows the reaction to occur. Essentially, any change that affects protein structure will affect the enzyme's catalytic function. So here we're looking at temperature and pH effects on enzyme catalysis. If you denature the enzyme, you lose all activity, because you lose all biological activity when you denature a protein. And you can denature with temperature or strong acids and bases, mechanical action, or some organic solvents. Here we see enzymes in the human body typically are modified to work the best at around pH of 7 to 7.4, which is what you find in the blood. Just slightly basic. As you get further away from that optimal pH, the rate of reactions decrease, and if the rate of reaction gets too low, a person will die because you can't do chemistry fast enough to maintain the state of being alive. Same with temperature. People are typically at 98.6. If you start getting away from that temperature, your chemistry starts slowing down, and at some point a person will die. There are some modified enzymes in the human body, like the enzymes that operate in your stomach. They prefer a pH of 2 because they've evolved to be effective in the acidic conditions of the stomach. And also with the temperature for the human enzymes, you don't have a nice even curve like this. It more resembles something like that, where here is normal human temperature. It does not take too much of a fever to kill you because your enzymes start slowing down rapidly. Whereas if a person is on a diet from hypothermia, that takes a lot longer. And so sometimes you might find a person who got lost outside and their body temperature is down 10 degrees and they still are alive because the chemistry actually slows down a lot slower as body temperature cools off. Whereas with the fever, it's like a cliff. It rapidly falls off. And so a temperature of 106 will kill a person. But when you're looking at hypothermia, a person can hold on for quite a while at an amazingly low body temperature sometimes. All right, if you plot the reaction rate of an enzyme-catalyzed reaction on the vertical axis and the temperature of the reaction on the horizontal axis, you will not get a straight line. And so again, if you plot the reaction rate of the enzyme-catalyzed reaction on the vertical axis and the temperature on the horizontal axis, you get a parabola because there's an optimal temperature. If we just plot it like this is like a non-biological reaction. In general, as it gets hotter, it goes faster, because that's just the base chemistry. However, when you're using an enzyme, that doesn't work that way, because if it gets too hot, you denature the enzyme, and then you lose all of your catalytic ability, and then you really then you drop down to normal chemistry, which is 1,000,000 times slower. And yes, that may get a little bit faster as you keep heating things up, but as you lost that 1,000,000-fold reaction rate from the catalyst, it still doesn't work. So again, if you heat up an enzyme too much, you destroy the enzyme and reaction rate plummets. And you can test that out at home with an egg. Boil an egg, the yolk changes. You've heated it up so much that all the proteins unravel and wrap around each other, and now you have a boiled egg yolk. Or it's like the difference between a raw potato and a cooked potato. In a raw potato, all the enzymes are completely active. They're still in their biological conformation. Whereas in a baked potato, they've all denatured and unraveled, and there is no catalytic ability left. Enzyme regulation. Enzyme catalysis is carefully controlled in cells. And we can modify them covalently by adding on a new molecule, like we talked about. Kinases add phosphates to molecules. Enzyme inhibition. These decrease the enzyme activity. And enzyme activation increase enzyme activity. And you can do both. You can make the enzyme work harder or work slower, depending on what you need. And our major types of control are through feedback inhibition. There is negative feedback and there is positive feedback inhibition. Most normal feedback inhibition is negative. And so the final product stops your initial enzyme. And therefore, your enzymatic system will make enough of a compound until it doesn't need any more, and then it'll shut off. And so in a system like that, you might have 4 enzymes, let's just say 3, and our substrate goes through 3 reactions and becomes our final product 4. And that will actually bind the first enzyme and shut it off. And that way, once you make enough of something, you shut off the machinery to not make any more, and you always have the right amount. Positive reinforcement, so instead of a negative feedback, a positive feedback system is unusual in biology, and is typically only encountered when a major event is going to occur, because the major event typically destroys the biological tissue which was sending the signal. And so good examples of positive feedback is childbirth and a woman expelling an egg out of an ovary. Those are positive feedback systems. However, most biological systems are negative feedback, and so the final product suppresses the initial enzyme. So in feedback inhibition, D here turns off the first enzyme, and that therefore, once you've made enough D, you shut the whole system off so that the cell is not wasting energy making a product that it does not need. And that is the end of the enzymes chapter.